Okay, so we're going to talk about now networking systems together. And this is kind of like it's going to serve as an introduction to TCP/IP. So basically, a network, the topology from the top down of a networking system is the communication architecture, which is software that would support communication between two independent computers. So you can have one computer that's running Windows operating systems and has Windows or Microsoft-based files. And then you could have another machine running Linux, which has Linux-based files. And they can send the files to each other or communicate, send messages to each other. They don't have to be the same operating systems. A network operating system is a configuration of networking applications, usually single server workstations and one or more server machines. And then we could also have a distributed operating system, which is an operating system that is scattered among machines that are on a network. Okay. So then the idea is we need a protocol. A protocol is a way for different machines to communicate to each other. And the way that different machines can communicate to each other, it's kind of like, a protocol is kind of like, you know, if I call you on the telephone and I dial your number, your phone starts to ring, you answer the phone, you say hello. So I wait for you to say hello, and then I say hello, it's me. And then you would say back to me, you know, I would identify myself, and then you would be ready to hear my message, and I would tell you what the point of my phone call is. And then we go back and forth, and eventually at the end of the phone call we say, okay, goodbye, and we hang up. So same thing is needed when two machines are talking to each other. So for example, if I want to send a message to Facebook, I want to log into Facebook. They don't know that I want to send a message to them, so they're just sitting there accepting messages from the whole world. And I need to connect to them, so I want to build a message that says, I am on my machine and I'm trying to connect to your machine and I would like you to respond to me. And when they receive the message, they're going to wake up and go, oh, this guy wants to talk to me, I guess I better respond to him. So same thing's kind of true in architectures. So the protocols are basically concerned with syntax, making sure every letter is perfectly correct, and the meaning, the semantics, and timing. So syntax is concerned with the format of the blocks of data we're going to send. So if I'm going to put an IP address in one field and an application number or a port number in another field, the receiver has to know exactly where to read. So the syntax has to be correct. The semantics, meaning the meaning of the message that I'm sending, has to be correct too. So a simple example of where semantics comes into play is, suppose I'm sending a message, but the message is so big, like let's say I'm mailing a big picture or a movie, and it has to be broken up into many messages. So I can say, well, here's part 1, and here's part 2, and here's part 3. If the receiver receives them in the wrong order and puts it together in the wrong order, it won't have the correct meaning. The data will have received, they would have received the data correctly, but when they put it together, it wouldn't have meaning. So I have to kind of say, this is part 1 and must go before part 2. I have to somehow communicate that, in addition to sending the movie. And then timing is also important. I don't know if you've ever sent a text message to somebody and you say, hey, do you want to go to lunch today? And they reply to you 4 days later, yes. You have friends who do that, right? Yes. And then, so the message has no meaning if a certain amount of time elapses that it loses its meaning. So we want to, you want to connect to Facebook. You don't want them replying 4 days later saying, what's your password? It'll be too late. So timing matters too. So a very popular protocol that is used in addition to just the IP protocol. The IP protocol, we'll kind of go into what the IP protocol is and then the TCP, which is running on top of IP is. But so a very popular way for two machines to be networked together is TCP/IP. So it stands for Transmission Control Protocol over Internet Protocol. As a little history, if you could Google and look up issue about how it came about. But it's a set of standards of things that you have to supply when you're sending a message over the internet to somebody coming back, for the message to come back to you. So TCP breaks up into, TCP over IP breaks up into different layers. The idea of what a layer is kind of like when you send when you're mailing a letter to somebody, how it gets transported to its destination, and how the person who actually receives the letter, how it gets to them, is, if you think about it, is done in layers. So suppose, for example, you wanted to send a letter from the United States to India, someone's house in India. So you would write your letter, the message you're trying to give, you're trying to write a message to somebody in India. You have to pick a language that both you and that person understand. You write the message in that language. So part of one layer is the language, right? Then you take the letter, you put it in an envelope. Well, that's another layer, an envelope around the letter. Then you start writing on the front of the letter, this is for such and such a person who lives in such and such a house, and that house is located in a certain town, and that town is located within a certain country, say India in this case. And then you go down to your post office and you put it in a mailbox, and you hope you put enough layers of information on it, it can get to the person you want it to go to. So the postman would look at it and go, oh, this is going to India, this has to get taken to the airport. Can't deliver this one by truck, has to be taken to the airport. Because the layer the country it's going to, well, there's a country layer, the country requires it to get on an airplane. Fly the letter over to India, then the person gets it off the airplane and says, this has to go to this town. The town is another layer. The house within the town is another layer. The person within the house is another layer. So you're just putting all these layers, you keep attaching all this information to your letter. In the end, your goal is to get the letter there, but you have to keep adding these layers. So the TCP IP layers are basically the application layer. So for example, if you're on a Windows machine, Windows operating system, and you bring up the Chrome application, that's Google's web browser. You bring up Chrome, or you could bring up Microsoft's Internet Explorer. Those are two different examples of applications. So you bring up an application, and that's what you type your message into. You say http://www.facebook.com. You hit enter. Your application is Chrome in that example. You have to connect your machine to the machine, the Facebook server, which is probably out in California. And a layer beneath Chrome has to find out what is the IP address of the machine in California and what is the application number that I'm sending my message to, and package that into your message. Then we're going to go from our machine, which is connected to the internet through that yellow cable. I don't know if you can see the yellow cable. It was always, the connection to the internet was always a yellow cable. Now they put up blue cables, which adds a little confusion. It's nice if it was always yellow. But anyway, we're going to send our message from this application. Then we get information on where it's going to go to Facebook, where the Facebook server is. We send it from our machine to our network here at the university. So it's going to go from our network, and it's going to connect from our network to Facebook's network, the network that Facebook is on. So once it gets from our network to their network, it has to get from their network to their machines. So the next layer is the internet layer. That's where we connect our network to their network. Then in communication from network to network is going to be handled with more information added to the message. So that would be like if we're sending bunches of blocks from our network to their network, how that gets coordinated. And then the physical layer would be how we're physically connected to the internet and how the messages are physically being transported. Are they being sent electronically, with electricity? Are they being sent optically? Do we convert the message into optics and send it through routers? So how the message is physically sent would also be, would be handled in data in the physical layer. So mailing a letter to India, the physical information might be, should it get on an airplane, or could it be sent by a truck alone? So that's kind of an analogy there. Okay, so just briefly going through each of the layers. The physical interface is basically like concerned with things like how the message is sent. Is it sent electronically? Is it sent optically? What's a good speed to send it at? If we send the message too fast and the receiver can't pick it up fast enough, they're going to lose a lot of data. So maybe we'll send a message to them saying, at what speed can you receive data from us? And then based on that speed, we'll start sending it to them. So information like that is handled at the physical layer. The network access layer, so we're working from the ground up. So that's the exchange of data between end systems and the network attached to them. So the physical address, the priority of the message, how big is each of the packets we're sending to them. We want to send a big message to them, but they have a fixed size that they receive messages at. We have to cut the message up, send it to them, and put information in the header like this is message 3 out of 10, and here comes message 4 out of 10. And so that information is handled at the network layer. The internet layer, this is where we're connecting our IP address to the IP address of the other machine. So here's where we would identify our IP address within our network, and we have the IP address of their machine within their network. So a router is a processor, if you think about it. Right? Cisco makes routers. But effectively, it's a processor. It could be a software or hardware processor. But it's a processor that connects two networks and performs the function of routing messages between them. So routers operate on the internet level. And then host to host, that would be actually our machine, its direct connection to Facebook's server, the application on that server, sending messages back and forth. So we might be concerned with things like reliability of our message. So we could send a message to them, and they receive it, but when they receive it, they're not 100% sure they got the full message. So maybe we could send some kind of error checking information to them. For example, we could send them a message, and in the end our message is going to be a bunch of zeros and ones. So let's say we send them 10,000 bits, zeros or ones, and let's say a little more than half were ones, 5,212 were ones, and the rest were zeros. We could send them a number like 5,212. So after they completely received the message, they could count up how many ones were in the message and see if it matches this additional number we send them, which is what we believe is the number of ones. And if it doesn't match, then they know they received a bad message. If it does match, does that mean they definitely received a good message? Would that definitely mean that they received a good message? If the number of ones, we send a message to them, we count up how many ones are in the message, and then we send a count, a number that tells them how many ones we send them. And then they count if that's how many they receive. So, okay. So, sorry. Right. Okay. And then the top layer, the application layer, is the layer in which, hi, oh, good. Hi. Okay. The top layer, the application layer, is the layer in which everything okay. Sorry about that. People taking pictures of the lecture. Okay. Okay, so the application layer would be the application that you, the user, are using to communicate to the internet. So, for example, when you bring up Chrome, Chrome is your application. So, for example, your web browser, any game you're playing that's connected to the internet, you're sending messages back and forth using that game, using that application. Okay. So the connection between your application and, let's say, here's Facebook, is you need to bring up an application, let's say application X, this could be Chrome. You need to build a message, and your goal is to send it from your application to Facebook's application, the web server that's going to send a message back to you. Well, in order to do that, you're going to build a message within Chrome. Chrome is then going to have to figure out, add another layer to it, add the TCP part of it, the transport layer information, how to get it from, you would fill in, for example, what application you are. I'm Chrome, and I want to talk to a particular application on Facebook server. So that gets filled in the TCP header data, that layer that you're adding on top of the message. Then it has to go from your machine, your IP address, to their machine. So in the IP block, you're going to put your IP address, and you're going to put their IP address. Then as it gets sent, maybe it gets sent in pieces, and there's timing information. That's going to be handled at the network layer. And then information about how you're physically connected to the internet gets added to the physical layer. Eventually, when your message gets built, it gets sent to your network. This is our network, let's say here at the university. Here's the network that Facebook is on. So we're going to send the message, this entire message that got built, we're going to send it across the internet to their network. Once it gets to their network, they're going to rip off all the layers and get it eventually to the application that it needs to go to. So this is, step by step. This all gets built on your machine before it gets sent out to your network. Your network then reads this information, sends it over the internet through routers to the network that Facebook is on. Facebook then rips off the headers and eventually gets it to the application it's going to. Same idea if you're mailing a letter from your house here in the United States to a house in India. You write your letter, you put who it's going to and where it's going to, what country it's going to. They figure out how to put it on the airplane and put it on a truck, and eventually makes its way to the person the letter's going to. Okay, so you have your original message. Your original message was sending to Facebook is we would like a web page that helps us gets us to log in. We then add the TCP header on, so that's going to be our application number, which is typically called a port number. I like to use the phrase application number, but unfortunately we're stuck with the name port number. But the port number is the application number. So when you are on Windows and you bring up Chrome, when Chrome comes up, you're asking the operating system, can you assign an application number or port number to this application? And there's 16 bits that we could use for the port number. So with 16 bits, we can have 2 to the 16 is 65,536 different applications running at once. So we assign a port number saying I am Chrome, and we can assign a sequence number like here's message 2 out of 10, and we could also put error checking into this header. So here's our original message, and then before we send it out to Facebook, we slap on a TCP header. And we could say, oh, we're sending 5,642 ones in our message, and then we write a number 5,642 here. So the receiver can count up how many ones they saw and see if it matches exactly, and feel very comfortable they got the correct full message. Then after we finish putting in the IP header information, we then add on the Internet Protocol information, which came out, those standards came out prior to TCP coming out. And that's where we put our IP address and the host's IP address, where it's going to, and if we're going to be expecting a reply, we should give our address so they can reply to us. And then network information on top of that as data is moving from network to network. Information that needs to be held there. So just to have an idea of what is inside these header fields, in the TCP header, that's really, application to application information. So we're going to put our 16 bits, right? So each row here is 32 bits, right? So this is bit 0 to 31. The first 16 bits of the header includes our application number, which we call the port number. So the number that uniquely identifies Chrome on our machine, in that example. So let's say our operating system assigned the number 3022 to Chrome. We would write 3022 here with 16 bits. We need to know the application on the Facebook server that we are sending information to. Well, we haven't even talked to them yet. We're just going to send a message to them. So how do we know what their application number is? We could go out to the internet and ask the internet, what is Facebook's IP address? But how do we know what the name of the web server, what is the application number or port number of the web server? So standards were made that says if you're looking for a web page, and if you bring up your web browser and you type HTTP with no S, http:// www.facebook.com, and hit enter. By typing in http:// you want port 80. 80 it was decided by the powers that be that port 80 is HTTP. So anytime you type in http:// www.facebook.com, your operating system can go out to the internet and ask what is the IP address of Facebook, and you know the port number is going to be 80. You don't have to ask, you don't have to send a message to Facebook saying what is the port number for the web server. It's already been pre-decided. And if you want to use HTTPS, which came out much later, they decided port number 443 was available, and they picked 443 for secure HTTP. So if you send a message to HTTPS, we know to fill in 443 right in these bits. Then there's other information. We'll go over like later on in the course what each one of these fields can do and what can go wrong if you don't set them correctly. But just to give, for now, just to have an idea of what is in these header files. The sequence number is if we're sending a series of messages, which one is it? Acknowledgement numbers could be used if we're sending transmission and we want to know that the receiver has received it. They can send information back to us. There's a field, these fields here, we can actually extend them if we decide for something related, very much related to this application. If we want to send more information, we can add more blocks of these, and we have to say how many there are. So we would put the size of the header in here. We only get 4 bits, so we can only go 1 to 15, 0 to 15. We could do things, we could also send a checksum number. We send them a number, which could be like the number of ones in the message. So they could then read the message after they receive it, count up all the ones, and see if it matches this number. So that's how some error checking is done. Was there a transmission error when we went from one, after we sent the message? So after this, so now we're back to here. So here's the message you're trying to send. This could be an email, it could be a movie, it could be a request to a web server saying, can I log into your website? You're sending a message. we put the TCP header on top of the message. Now, after the TCP header is on, we're now going to put another header on. So this is again the TCP header. We fill in this data. And when we start talking about like socket programming, well, so one thing we could do is we could go get storage and fill in the bits, zeros and ones, and then slap it onto the message and send it out. And you could also do socket programming, which is where your operating system provides methods that will basically fill in these blocks for you. And then you can send your message out. So that's a little more convenient, because you may miss a field or put 33 bits here, and then it throws off all your other bits after it. So sometimes good to just use operating system provided socket software when creating these fields. Okay, so we take your message, we put a TCP header on in front of it, fill it in with some data that connects your information about how to connect your application to the application on the destination machine. Now we have to connect your machine to their machine. So we slap on another header called the IP header. So I think we talked about, when we were talking last class about IP addresses, we talked about how there were 4 versions of the Internet Protocol. When they got to the 4th version, they said, oh, this one's good, this one will last forever. And this is a protocol that uses 32-bit numbers to identify every machine on the Internet. So that gives us 2 to the 32, which is a little over 4 billion machines can be connected to the Internet, which back in the 1980s was a lot, but today it's not a lot, because there's like 8 billion people in the world or 10 billion people in the world, so it means each person can have a half a connection to the Internet. And right now everyone has tons of connections to the Internet. You probably have a few right now in front of you, okay? Your cell phone, your laptop, you probably have using up 3 IP addresses right now. Okay, but anyway, so here's the version 4 example. And for example, we give 32 bits for our source IP address, and another 32 bits for the IP address of where the message is going to. So we would put Facebook's IP address here. We would put our IP address here. And we have another checksum field. And like I say, we have a total length of the message, so we can add more layers of these options and padding. So we can make the message bigger if there's something very special about our transmission to them. And we can also, in the IP, we can say how much time this message has to be alive. So like say when you say to your friends, do you want to go to lunch today? Well, this message is only good for about an hour or 2. After an hour or 2, whether they answer yes or no, the message has expired. Right? So we can put in a field that says how long until you get a response, and otherwise we're not interested in the response. Okay. Version 6, IP version 6, which is the new one that's taking into account that, we need a lot more IP addresses than, the world needs a lot more IP addresses than 4 billion. They're going to a new format where IP addresses are 4 times the size. So instead of being 32 bits, they're 128 bits. So we have to have much more for these source and destination addresses. So without disturbing the TCP part, we're able to expand the IP part. So it's kind of good that that was done in 2 different parts. So all the TCP code that's out there doesn't need to be changed, but now this has to be swapped in all messages. Okay, so that's basically just an introduction to networking, the idea of what's involved when you're trying to send a message from your computer, from an application on your computer to an application on another computer. What's involved in getting the message over there and how it comes back. There is another protocol following the OSI model, and we can talk about that on another class. Instead of having 5 layers, it has 8 layers. So some of the layers of the TCP have basically been broken up into 2 separate sections because, it was just later decided that could work better. So they have, it starts at the application level. then breaks into pieces along the way and eventually gets down to the physical layer. But they just have a little, they broke it out a little bit more. Might slow down the transmission of the message, but might make it more reliable or a better system. Could be an argument for it. Okay, so does anybody